Welcome back to our final lesson for material balances. I want to remind you that these topics, we're only skimming the surface. We're just doing enough so that we can get through material balance problems, and you'll be doing more with this in future courses as you study thermodynamics. So today we're going to be talking about liquid-liquid equilibrium. Now, this is a technique that can be used to separate mixtures that are in a liquid. So if we have a miscible simply is fancy talk for things that can mix together. Okay, so a miscible mixture of A and B, so they are together as one liquid. And we really want pure A. The idea is that we seek out the perfect chemical C, where B is more soluble in C than it is in A. But A and C are immiscible. So immiscible means they don't mix. And in that case, then we would be able to say that, oil and water don't mix, right? But water and vinegar do mix, so they would be a miscible mixture. So if we found the right oil to add to our oil, or our water and vinegar, then we might be able to separate those out. The way we would do this is you have A and B, you add C, you shake it really good, and then you give it enough time to separate the two liquid phases. So B, that was formerly with A, preferentially is now with C. It just likes C better. And now you can decant that off. You have pure A and you have a little cup of B and C mixed together somewhere else. So this is a purification technique that will be used on occasion. And so we need to be able to discuss and analyze these kinds of systems also. So 3-component mixtures are going to be the key to understanding these, and they tend to be graphed on a triangular composition diagram. Now, this is an example of one of these. They can be isosceles triangle, or they can be done on a right triangle. Okay, these tend to be done more frequently these days. They're a little bit newer. Things will tend to use this simply because Excel will create one of the right triangle ones. These are a little bit more complicated to create, but they are conceptually easier and everything feels more equivalent. But the idea is that in the corners, you have your pure substances identified. Okay, and that would be the same for either type of diagram. In the corners, you would identify pure substances. And each point inside the diagram represents a different ratio of those 3 components. So if I have pure acetone here, this line is 95% acetone, 90%, 85%, all the way down until we reach this line, which is 0% acetone. And I can do a similar thing for my water. Water is here is pure. This is 95% water, 90%, 85%, all the way down to this line, which is 0% water. And similarly for the MIBK in the other corner. Now, that means that if I were to look at any particular point, so let's take this point right here that's labeled K, I would read that. So from this direction tells me how much acetone, and so this is 65% acetone. Reading this direction tells me how much water. It's 15% water. And the remaining part is going to be MIBK, but let's read it off the graph. So MIBK, I read that direction. So 5, 10, 15, 20, 20% MIBK. And that is this point on this graph right here. One of the key things is, and my artwork is a little bit off when I did the PDF of this, but up in this region here, I have just a single phase that's formed. It's going to be a liquid and just one single liquid. So that point we just found, K, is going to be a liquid with that composition we just talked about. This part down here, underneath this dome, this part is going to be two liquid phases. The two liquid phases are going to be in equilibrium, but they're going to have different compositions. So for this point M, if I gave a mixture with point M, which has, again, let's practice, acetone, it's 15% acetone. It's 55% water, and the balance 30% MIBK. But if I put that in there, what I see is that it's in this two-phase region, and it's going to split into two different liquid phases, something like oil and vinegar and salad dressing. And those are going to be represented by the tie line. And so I read across to find a tie line. And my two different phases are going to be the endpoints of that tie line where it crosses the dome. Okay? And so one of my liquid phases is going to be about 12% acetone and close to 85% water and about 3% MIBK. And the other solution is going to be about 18% acetone, about 5% water, and close to 73% MIBK, whatever adds up to make that 100%. So, yes, just showing you another point there. This point right here is a liquid mixture, and it forms one single phase. This down here forms a liquid that splits into two phases, okay, that follow the tie line, and that's the worst tie line I've ever seen. Now, there's a video lesson on the Learn Chemie website that will go through this, but you can do material balances based on the mass you have fed into the system and how much is on either end of the tie line, okay, and what those compositions are. And you can do material balances, and they will lead to something that's called the lever rule. I'm going to ask you to watch that other video. It's a little bit of a lengthy derivation, but the idea is, okay, you guys have played seesaw before, I hope. The idea is, okay, if you have two little children, and I have a little teeny kid and I have a great big kid, okay, and they want to play seesaw together, which one of them do I want to be, closer to the fulcrum, okay, and which one do I want to be further away, okay? So in this particular case, I would want to have, okay, try to remember doing this, okay, I need to put more weight on the short side, okay, and less weight on the long side. The idea is that this length here is proportional to his weight as this one is to the length of this one. Okay, so how that works for us. If I look at the length of this line, and I'll designate this length 1, okay, and the length of this line, L2, okay, L1 over L2 is going to be proportional to, or as fractions equal to, L1 is going to tell me how much and L2 is going to tell me how much. Again, I highly recommend that you go through and look at that other video.